Section: Contents. In this section, we demonstrate that we can transfer the reasoning abilities of larger models into smaller ones, leading to improved performance compared to smaller models trained through reinforcement learning. We introduce DeepSeek-R1, an open-source tool that will aid the research community in creating better smaller models. By using the reasoning data from DeepSeek-R1, we fine-tuned several popular dense models, and the results show that these distilled smaller models excel on various benchmarks. For instance, DeepSeek-R1 Distill Qwen 7b scored 55.5% on AMY 2024, outperforming a larger model, while DeepSeek-R1 Distill Qwen 32b achieved 72.6% on AMY 2024, 94.3% on Math 500, and 57.2% on Live Codebench, significantly exceeding previous open-source models and matching a mini-model. We have made available distilled checkpoints of various sizes, including 1.5b, 7b, 8b, 14b, 32b, and 70b, based on the Qwen 2.5 and Llama 3 series. In our evaluation summary, we found that DeepSeek-R1 scored 79.8% on AMY 2024, slightly better than OpenAI 1217, and achieved an impressive 97.3% on Math 500, matching OpenAI -1217 while outperforming other models. In coding tasks, DeepSeek-R1 reached an ELO rating of 2029 on Codeforces, surpassing 96.3% of human competitors. For engineering tasks, it performed slightly better than DeepSeek v3, aiding developers in real-world applications. On knowledge benchmarks like MMLU, MMLU Pro, and GPQA Diamond, DeepSeek-R1 excelled with scores of 90.8%, 84.0%, and 71.5%, respectively, outperforming DeepSeek v3 and showing competitive performance against other closed-source models. In fact-based queries, it also outperformed DeepSeek v3 on simple QA. Moreover, DeepSeek-R1 showed strong capabilities in creative writing, general question answering, editing, and summarization, achieving a win rate of 87.6% on Alpaca Eval 2.0 and 92.3% on Arena Hard. It also excelled in tasks requiring long context understanding, significantly outperforming DeepSeek v3. We note that previous research relied heavily on large amounts of supervised data to boost model performance. In our study, we show that reasoning skills can be enhanced through large-scale reinforcement learning without needing supervised fine-tuning as a starting point. We also found that adding a small amount of cold start data can further improve performance. We present two approaches. 1. DeepSeek-R1 0, which applies reinforcement learning directly to the base model without any supervised data, and 2. DeepSeek-R1, which uses reinforcement learning starting from a checkpoint fine-tuned with numerous long chain of thought examples. In exploring DeepSeek-R1 0, we focus on the potential of large language models to develop reasoning skills purely through reinforcement learning, without relying on supervised data. We provide an overview of our reinforcement learning algorithm and share some exciting results, hoping to offer valuable insights to the community. To reduce the training costs associated with reinforcement learning, we utilize group relative policy optimization, which eliminates the need for a critic model of the same size as the policy model and instead estimates the baseline from group scores. Section Summary. In this section, we demonstrate that larger models' reasoning patterns can be effectively distilled into smaller models, leading to superior performance on various benchmarks, including AMY 2024 and Math 500. We introduce DeepSeek-R1 and its distilled versions, which outperform previous models and provide open-source checkpoints to facilitate further research in model distillation. Section: Reward Modeling. In this section, we discuss the reward modeling for training DeepSeek-R1 0. The reward serves as the training signal that guides the optimization in reinforcement learning, RL. We use a rule-based reward system with two main types of rewards. First, we have accuracy rewards, which assess whether the model's response is correct. For instance, in math problems with clear answers, the model must present the final answer in a specific format, allowing for straightforward verification. For coding challenges like those on LeetCode, we can use a compiler to provide feedback based on set test cases. Second, we implement format rewards, which require the model to enclose its reasoning process within specific tags. We chose not to use a neural reward model for DeepSeek-R1, as we found it could lead to reward hacking during large-scale training, complicating the process and requiring extra resources for retraining. To train DeepSeek-R1, we start with a simple template that directs the model to follow our instructions. This template asks the model to first outline its reasoning and then provide the final answer. We intentionally keep our constraints focused on structure, avoiding biases related to specific content or problem-solving methods, so we can accurately track the model's natural development during RL. We also present the performance of DeepSeek-R1, which shows a steady improvement on the AIME 2024 benchmark throughout the training. The average pass rate increased significantly from 15.6% to 71.0%, reaching levels similar to OpenAI's model. This improvement demonstrates the effectiveness of our RL algorithm in enhancing the model's performance over time. Our comparative analysis shows that RL enables DeepSeek-R1 to develop strong reasoning skills without needing supervised fine-tuning data. Moreover, we found that using majority voting can further boost performance. For example, on the AIME benchmark, applying majority voting raised the score from 71.0% to 86.7%, surpassing OpenAI's model. This indicates that DeepSeek-R1 has a solid foundation and potential for further advancements in reasoning tasks. We also explore the self-evolution process of DeepSeek-R1, which illustrates how RL can help a model autonomously enhance its reasoning skills. By starting RL directly from the base model, we can observe its development without the influence of supervised fine-tuning. The model shows consistent improvement in thinking time, which is a natural progression rather than a result of external changes. DeepSeek-R1 learns to tackle more complex reasoning tasks by utilizing extended test time computation, generating numerous reasoning tokens to refine its thought processes. One fascinating aspect of this self-evolution is the emergence of advanced behaviors, such as reflection and exploring different problem-solving methods, which arise as the model interacts with the RL environment. These behaviors enhance DeepSeek-R1's reasoning capabilities, allowing it to address more challenging tasks effectively. Finally, we note a particularly interesting phenomenon during training known as the aha moment. This occurs in an intermediate version of the model, where DeepSeek-R1 learns to spend more time thinking about a problem by reassessing its initial approach. This behavior highlights the model's growing reasoning skills and exemplifies how RL can lead to unexpected, sophisticated outcomes. The aha moment not only signifies a breakthrough for the model but also for us as researchers, showcasing the potential of RL to foster advanced problem-solving strategies autonomously. This moment serves as a reminder of the possibilities that RL holds for developing more intelligent and adaptive artificial systems in the future. Section Summary. In this section, we describe how we train DeepSeek-R1 using a rule-based reward system that includes accuracy and format rewards, enabling the model to improve its reasoning capabilities autonomously through reinforcement learning. We highlight the model's significant performance enhancement on the AIME 2024 benchmark, its self-evolution process that fosters sophisticated problem-solving behaviors, and the emergence of an aha moment that showcases the model's ability to adapt and refine its strategies independently. Section: Drawback of DeepSeek-R1. In this section, we discuss the limitations of DeepSeek-R1. While it shows impressive reasoning abilities and can develop strong reasoning behaviors on its own, it has issues such as poor readability and language mixing. To enhance the clarity of reasoning processes and share them with the community, we introduce DeepSeek-R1, which uses reinforcement learning, RL, with user-friendly cold start data. We are motivated by two key questions. First, can we improve reasoning performance or speed up convergence by using a small amount of high-quality data as a cold start? Second, how can we create a model that generates clear and coherent chains of thought, COT, while also demonstrating strong overall capabilities? To tackle these questions, we have designed a 4-stage training pipeline for DeepSeek-R1. In the cold start phase, we avoid the instability seen in DeepSeek-R1 by collecting a small set of long COT data to fine-tune the model as the initial RL actor. We gathered this data through various methods, including few-shot prompting, prompting models for detailed answers, collecting outputs from DeepSeek-R1 in a readable format, and refining these results with human annotators. We amassed thousands of cold start samples to fine-tune the DeepSeek v3 base model. The advantages of using cold start data include improved readability, as we designed a format that includes a summary at the end of each response and filters out unreadable outputs. We define our output format as a special token followed by the reasoning process and another special token followed by the summary. Additionally, by carefully crafting the cold start data, we observed better performance compared to DeepSeek-R1, supporting our belief that iterative training is beneficial for reasoning models. Next, we focus on distillation to enhance smaller models with reasoning capabilities similar to DeepSeek-R1. We fine-tuned open-source models like Qwen and Llama using 800,000 curated samples. Our results show that this straightforward distillation method significantly boosts the reasoning abilities of smaller models. We used various base models, selecting LLAMA 3.3 for its slightly better reasoning capability. For the distilled models, we applied only supervised fine-tuning, SFT, without including an RL stage, as our main goal is to showcase the effectiveness of the distillation technique. We evaluated our models using several benchmarks, including MMLU, MMLU-Redux, and others, as well as open-ended generation tasks with LLMs as judges. We followed the original configurations for evaluations, ensuring to avoid length bias by only providing the final summary. For distilled models, we reported results on key benchmarks like AMI 2024 and Codeforces. In terms of evaluation prompts, we used standard benchmarks and modified prompts as needed for different datasets. For code and math benchmarks, we utilized the Human Eval MUL dataset covering various programming languages. We evaluated model performance on Live Code Bench using the COT format and assessed the Codeforces dataset with expert-crafted test cases. Finally, we capped DeepSeek-R1 outputs at a maximum of 32,768 tokens for each benchmark. Section Summary. In this section, we discuss the limitations of DeepSeek-R1, such as poor readability and language mixing, and introduce DeepSeek-R1, which utilizes reinforcement learning with cold start data to enhance reasoning clarity and performance. We outline our training pipeline, which includes collecting high-quality cold start data to improve model outputs and demonstrate the effectiveness of distillation techniques for smaller models, while also detailing our evaluation methods across various benchmarks. Section: Baselines. In this section, we conduct thorough evaluations against several strong models, including DeepSeek v3, Claude Sonnet -3.5-1022, GPT 400513, OpenAI, Mini, and OpenAI -1217. Due to difficulties accessing the OpenAI -1217 API in mainland China, we base its performance on official reports. We also compare the open-source distilled model -32B preview. For our evaluation setup, we set the maximum output length to 32,768 tokens. We noticed that using greedy decoding for long output reasoning models led to higher repetition rates and variability across different checkpoints. Therefore, we default to a pass at K evaluation method, reporting pass at 1 with a non-zero temperature. Specifically, we use a sampling temperature of 0.6 and a top p-value of 0.95 to generate between 4 and 64 responses for each question. Pass at 1 is calculated as the average correctness of these responses. This approach gives us more reliable performance estimates. For AIME 2024, we also report consensus results using 64 samples, referred to as cons at 64. In our evaluation of DeepSeek-R1, we find that it outperforms DeepSeek v3 on education-focused benchmarks like MMLU, MMLU Pro, and GPQA Diamond, mainly due to better accuracy in STEM questions achieved through large-scale reinforcement learning. DeepSeek-R1 also excels in frames, a long context QA task, showcasing its document analysis strengths. On the factual benchmark Simple QA, DeepSeek-R1 again surpasses DeepSeek v3, demonstrating its effectiveness with fact-based queries. We observe a similar trend where OpenAI surpasses GPT-4o on this benchmark. However, DeepSeek-R1 underperforms compared to DeepSeek v3 on the Chinese Simple QA benchmark, mainly because it tends to refuse certain queries after safety reinforcement learning. Without this safety measure, DeepSeek-R1 could achieve over 70% accuracy. Additionally, DeepSeek-R1 performs well on if-eval, which assesses a model's ability to follow format instructions, thanks to the inclusion of instruction following data during the final stages of training. We also see strong performance on Alpaca Eval 2.0 and Arena Hard, indicating DeepSeek-R1's strengths in writing tasks and open domain question answering. Its significant improvement over DeepSeek v3 highlights the benefits of large-scale reinforcement learning, enhancing reasoning capabilities and performance across various domains. Moreover, the summaries generated by DeepSeek-R1 are concise, averaging 689 tokens on Arena Hard and 2,218 characters on Alpaca Eval 2.0, showing that it avoids length bias in evaluations. In math tasks, DeepSeek-R1 performs similarly to OpenAI 1217, significantly outperforming other models. We see a similar trend in coding algorithm tasks, like Live Code Bench and Codeforces, where reasoning-focused models excel. In engineering coding tasks, OpenAI -1217 outperforms DeepSeek-R1 on AIDR but matches its performance on SWE verified. We believe that the engineering performance of DeepSeek-R1 will improve in future versions, as the current amount of related reinforcement learning training data is limited. Regarding distilled models, we find that simply distilling DeepSeek-R1's outputs allows the efficient DeepSeek-R1 to 7b to outperform non-reasoning models like GPT-400513. DeepSeek-R1 to 14b surpasses -32b preview across all metrics, while DeepSeek-R1 to 32b and DeepSeek-R1 to 70b significantly exceed Mini on most benchmarks, demonstrating the strong potential of distillation. We also discover that applying reinforcement learning to these distilled models leads to further gains, which we believe merits further exploration, so we present only the results of the simple SFT distilled models here. In comparing distillation and reinforcement learning, we see that distilling DeepSeek-R1 allows smaller models to achieve impressive results. However, we question whether a model can reach similar performance through large-scale reinforcement learning without distillation. To investigate this, we conduct large-scale reinforcement learning training on Qwen 32b base using math, code, and STEM data for over 10,000 steps, resulting in DeepSeek-R10 Qwen 32b. Our results show that this 32b base model achieves performance comparable to -32b preview after large-scale reinforcement learning. However, DeepSeek-R1 distill Qwen 32b, which is distilled from DeepSeek-R1, performs significantly better across all benchmarks. Thus, we conclude that distilling more powerful models into smaller ones yields excellent results, while smaller models relying solely on large-scale reinforcement learning require substantial computational power and may not match the performance of distilled models. Additionally, while distillation strategies are both economical and effective, advancing beyond current intelligence limits may still necessitate more powerful base models and larger-scale reinforcement learning. Section Summary. In this section, we evaluate DeepSeek-R1 against several strong baselines, demonstrating its superior performance on various benchmarks, particularly in STEM-related questions and long context-dependent tasks. We also find that distilling DeepSeek-R1 into smaller models yields impressive results, outperforming non-reasoning models, while large-scale reinforcement learning alone does not achieve comparable performance without distillation. Section: Unsuccessful Attempts. In this section, we discuss our unsuccessful attempts during the early development of DeepSeek-R1. We share these experiences to offer insights, but we do not suggest that these methods are ineffective for creating reasoning models. For the process reward model, PRM, we found it to be a reasonable approach for guiding the model in reasoning tasks. However, we faced three main challenges. First, it was difficult to define specific steps in general reasoning clearly. Second, assessing whether an intermediate step was correct proved challenging. Automated annotations often fell short, and manual annotations were not scalable. Third, introducing a model-based PRM led to reward hacking, requiring extra training resources and complicating our training process. While PRM can help rank responses or assist in guided searches, its benefits are limited compared to the extra computational demands it adds during large-scale reinforcement learning. Regarding Monte Carlo tree search, MCTS, inspired by AlphaGo and AlphaZero, we aim to improve scalability during testing. This method involves breaking answers into smaller parts, allowing the model to explore solutions systematically. We prompted the model to generate multiple tags for specific reasoning steps. Initially, we used collected prompts to find answers through MCTS, guided by a pre-trained value model, and then trained both the actor and value models with the resulting question-answer pairs. However, we encountered challenges when scaling this training. Unlike chess, where the search space is well defined, token generation creates a much larger search space. We set a maximum extension limit for each node, but this sometimes caused the model to get stuck in local optima. Additionally, the quality of generation is heavily influenced by the value model, which is difficult to train finely. While AlphaGo succeeded by progressively enhancing its value model, we found this principle hard to apply due to the complexities of token generation. In summary, while MCTS can enhance performance during inference with a pre-trained value model, improving model performance through self-search remains a significant challenge.